I wish my introduction yesterday was as eloquent and comprehensive. And I am totally put to shame. And thank you so much for all the kind words. So yeah, this is true. And the book is not fake. And I have one here just so that you would believe me for sure. And as a good tradition, I will give this copy to the person who asks the best question. And I know that Joran is already competing with everybody who wants to ask some questions. So who knows Borges and the Garden of the Forking Paths? So, OK, yeah, a couple of people do. All right, so we can draw a parallel between fuzz testing and Borges's Garden of Forking Paths short history. So Borges introduces us to the idea of infinite labyrinth of possibilities where numerous paths unfold and intersect both in space and time. Similarly, I think that fuzz testing explores the never-ending labyrinth of possibilities and where we try to uncover bugs and issues in software. This metaphor underscores our approach in fuzz testing, navigating through the myriad of potential paths and trying to find the most interesting and critical ones. This process highlights the complexities of software testing and elusive nature of bugs. And this is very similar to how labyrinths symbolize the complexities in reality in Borges' story. So in this talk, in his talk yesterday, Kyle mentioned weird transaction spaces. And today, someone said, how much of a universe have you already explored? So that was in a question. And I'll do my best to tell us how to explore those weird spaces and how we can squeeze the most out of our fuzzer. So in order to set a little bit of expectations for you to understand what this talk is going to be about, so testing is an extremely, extremely broad subject. And there are as many approaches to testing as there are people. And one of the important approaches in testing is a compatibility with an existing consistency model. Because this means that we check whether whatever we advertise is also true in the reality. Usually, such tests can do away with relatively simple inputs, and then we track database responses and check if these responses exhibit any anomalies. By the way, by no means I'm trying to trivialize this. This is a very hard job, and it's just not exactly requiring any complex inputs in the first place. So for example, linearizability checker will report a linearizability violation if it finds that the results of an operation did not become visible, for instance, after the observed completion. And there are speakers on this conference who are way, way, way better equipped than I am to talk about these things. So I'm going to focus on some others. Since checking for a consistency model primarily focuses on finding like concurrency, timing, liveness issues, it is often using sort of like simpler, smaller values, and often even something like a monotonically incremented counter can be already useful. Of course, linearizability issues can still be a result of a logic bug, and today we're going to be mostly talking about logic bugs, or going to be focusing on those. The idea still remains the same. More often than not, you do not need any sophisticated input, and most sophistication is required for building and some interesting and tricky interleavings that will lead to some non-trivial result. I believe that things we'll be talking about today are also applicable in some ways to this area, but this is not going to be a primary focus. So similarly, there are many people who have a lot of experience in deterministic simulation around here, and I will let them to cover this subject extensively. And for the purpose of this talk, I just wanted to quote the definition of DST from one of my favorite books. It's Jim Gray's 1992 Transactional Processing. And I think that, first of all, it's striking that it's so early that it was summarized, and it was summarized pretty well. The model describes each aspect of the system, storage, processor, communication, by presenting a program that simulates the behavior of such entities, complete with their failure characteristics. For example, a storage module reads and writes data at storage addresses, but it also occasionally writes the data to the wrong place, invalidates pages, or damages the whole store. It's a pretty good explanation, right? So what's interesting, that it describes chaos testing, failure injection, and many other things. And here, the author does not explicitly say that it is going to be deterministic, but there is a paragraph right below which says, imagine that each process is implemented by a lower level automaton, I think it's deterministic, that usually executes the next step of the process, but sometimes stops the process execution for repair period, discards all the process messages, resets the process initial state, and then continues the process execution from the initial state. So that talks a little bit about determinism. So let's read on. He says the presentation then models a process and messages. Messages can be lost, duplicated, delayed, and corrupted, and permuted. So again, a bit more of that. Anyways, this is all very intriguing, isn't it? And while I believe that deterministic simulation is extremely important, the classes of issues that I am going to talk about today may not always benefit additionally from deterministic simulation. In other words, many issues can be found instably reproduced by just a single threaded execution, and reproducing them does not necessarily rely on very weird and complicated to reproduce thread interleaving. So of course, this is not due to any fault of deterministic simulation, and my point here is simply that you can benefit from the approaches I'll be describing, even if you do not have a deterministic simulation. And quoting Gray yet again, I will mention that probably we're going to be focusing more on Bohr bugs and not on Heisenberg bugs, and the bugs that have inherently deterministic behavior. Yeah, rather than Heisenbergs that have bugs that have more of a transient nature. So we're going to be focusing on finding the bugs and issues, but what does constitute a bug? I will be quoting Gray a lot today, so stay put. So we say that the bug is when the module behavior deviates from the specified behavior. It means that every action in your system should have some predetermined and defined result. And exercising the action should always yield this result, and any deviation from this will constitute a bug. So of course, to be able to do this, you first have to have a deep understanding what the expected behavior is. But most of the time, this is not a problem. And the problem is to describe this behavior precisely. Unlike good and friendly actors who will mostly exercise the happy path, our goal is to find ways to make the system deviate from these behaviors. So we're lucky if the system can tell us that something is wrong with it. In other words, we can trigger some null pointer exception, some assertion, or make it throw an exception. In such cases, all we need is to create interesting inputs, and the system will tell us that, OK, something went wrong. And unfortunately, this is not always the case. So not all of the bugs are, the system is not going to notify us about every single issue that it is experiencing. And we definitely would prefer to catch these exceptions in testing, but not in production. And even though this is our preference, I would say that good alerting will give us a proper heads up about their existence. And the trickiest and scariest classes of issues are the silent ones. So whenever we have a silent data loss or data resurrection issue, whether it's transient or permanent. And operators cannot be easily identified about their existence, and they will mostly be found by customers who, and often not even by the users of the database, but by the customers who are experiencing the data loss on really real customers, right? Not just the internal users of your database in your company. So when such issue is found, the impact might be difficult to evaluate since it may have been manifesting for days, weeks, or even years before it got found. So in order to find such issues, we need a model for the database behavior that makes it possible to predict query results and checking them against the actual ones. So I'll tell you how we are modeling Cassandra behavior in just a couple of slides, so stay put. To find such logic bugs, we need to be creative, right? Because they don't just jump on us. We need to explore the vast space of database states and navigate it in order to trigger interesting ones. So, of course, we will depend on randomness here, but simply generating random queries is going to burn extremely a lot of resources. So it is not enough to do that. Instead, we will need to guide our search and make our fuzzer explore interesting paths and different behaviors. We can and should depend on human input and human intuition for exploration and make it possible for developers to express different things or different behaviors efficiently. So tests oftentimes build on top of each other, meaning that you could reuse some of the functionality of the previous test. So we need our fuzzer to be built in the way that will make it easier to reuse all this functionality. So the logic bugs. Let's talk in more details about the logic bugs and how they manifest. I'll bring some of the examples of what we were able to find in Cassandra. We'll focus on the bugs which are manifesting in a way that, like something related to availability or visibility of data, which is not always necessarily a part of the consistency model, even though under some circumstances this is a consequence of that. So if you are, for instance, paging through the results, and you see 10 rows if the page size is 5, but only 9 rows when the page size is 1. This is a transient data loss issue. In such case, paging logic may hit some edge condition that doesn't correctly account for certain page sizes. This is horrible. Another example is a difference in a result depending on whether the data is read from disk or from memory. It can trigger the change in behavior whenever you flush your mem table, for instance, in Cassandra to disk, and you sort of like lose your data after it went from memory to disk. Horrible as well. There could be a race condition that makes the coordinator ignore the results that were delivered by some replicas. So this is more transient and elusive. I would say that something like this is more likely to manifest in a transient way. And I still think that, at least in the instances I have seen, this was still a logic bug, so a logic issue. So while it is scary to lose the data, it may be equally bad whenever something that you have deleted has reappeared after deletion. So in Cassandra and many other distributed databases, deletions are expressed as tombstones. So data resurrection is sort of a form of a data loss. So basically you lose a tombstone and therefore you're sort of like resurrect the data, even though I would argue this is also some form of a data loss. And since data is often opaque from the perspective of the database, it is hard for the database to tell you that, hey, I lost some data. So it is only you as a developer or a person who is using your database can tell that, hey, this should have been there and it's not, so it's a problem. So we rely on an external observer. So the database bugs are tricky, and even though they manifest as data loss, actually understanding the reason for them is tricky and often unintuitive. The tricky issue was caused by the condition that was, for instance, resetting the tombstone boundaries when switching pages. It was very difficult to debug, however, was relatively simple to reproduce. And since only few situations applied to this condition, it was difficult to sort of like get the system into the state where we would trigger it, but whenever we could trigger it at will at whatever time. So yeah, it was a deterministic issue that was difficult to find, but after we found it, we could trigger it at any point in time. One common issue with such bugs is that they may be somewhat difficult to shrink, or at least I could not find any automated way to shrink such things. So just a refresher, shrinking is a process that reduces the number of steps that is required to reproduce the issue by eliminating the steps that did not necessarily contribute to the issue, at least, well, to the degree that is possible. So an ideal shrinker will give you a minimal possible number of steps that will reproduce the bug. But of course, in reality, shrinkers more often than not will give you still a few steps, a few extra steps, because they cannot reliably eliminate everything else. So I think that validation logic in software can be sort of like broken down in two components. The first one is generating steps that lead to interesting scenarios. And the other one is modeling system behavior in a way that faithfully represents the states that the database is going to be producing. Surprisingly, there are very few examples of the project that can actually perform verification of query results. So there is a popular project which is called SQL Lancer that was developed specifically for testing for database logic issues. And it is relying on narrowing down query results. Sometimes they also do comparison of optimized and non-optimized queries, but they also do pivot queries, which means that you make a wider query and then you narrow it down, and you know that a subset is a subset of a superset. Sort of tautological, but you get the gist. So, of course, such approach can find to help many issues, but unfortunately, there is an entire class of the problems that cannot be covered by this approach. And one of the things that cannot be found is validating the results of arbitrary queries when you cannot have the system under test itself as a source of truth, because we know that in some cases our database may be lying to us by not delivering the results that we want. But what if we actually did have a trusted oracle that can give us a state of our database systems, but does not require a standby copy of it right next to it, right? So the simplest way to do this is something that is called invariant testing, and it is using internal consistency principle for the data. So for example, we can always insert and delete rows pairwise, which means that existence of one of the rows automatically implies the existence of the other. So if you see that the other one is not present, then you know that there is a bug. So this approach requires us thinking through the data generation and implanting some syntactic invariants into the data, and then using the internal consistency rules for the validation. So unfortunately, something like this sort of limits us in terms of what specifically we can generate in the end, and this limits our exploration. There may be entire classes of issues, again, which cannot be covered by this approach. And what is great, though, about this form of testing is that it's super easy to start with. You come up with an invariant, and you check it, and every violation is something for you to spend the night on investigating. So an alternative to designing such system by creating is design a system that has an oracle that will understand the same exact inputs as the system under test itself, and in some form have like internal state representation. So whenever we run an insert query or an update query, whatever, against our database, we also apply the same query to the oracle. Then when we run a select, oracle predicts the result that is going to be returned by the database. In this way, we can compare two results returned by the system under test and by the oracle, and investigate all the discrepancies between the two. Again, something fun to do at night. So unfortunately, a trivial implementation of an oracle isn't without its own problems. So one obvious problem with oracle testing is that, first of all, we need to implement most of our database logic inside our model checker. So another thing is that we need at least as much state inside our oracle as in the database, right? Because, I mean, we just want to check whatever is in database, so we need another copy of it. So it's sort of like an equivalent of a standby copy. So one of the reasons that we may need more information in the oracle than in the database itself is, for example, for checking for the deleted data, right? So if you want to know that something is not present in the database, you need to know what to look for. So you have to record the deleted rows as well, and then ask the database that, OK, are you sure that you don't have them? And the database should say, OK, I don't, and then it's good. So lastly, we need to have at least some form of quiescence in Oracle testing. I know it's a far-fetched word in this context, but I could not find a better one to express what I had in mind. So the state should be accessible as of some timestamp of a read, right? So because we cannot simply stop the world completely and make the database sort of not apply any queries while we are verifying the results. So we need some form of Oracle that can either have snapshots or be able to produce the result depending on like when exactly the query has started and ended. So gladly, all of these problems are relatively simple to solve. Instead of implementing entire database, we can use simple integers and like smaller values to represent the database state instead of like large strings or byte arrays or whatever. This means we will not have to implement any database logic for like integer and then implement the same for Booleans and then implement the same for byte buffers and stuff like that. All of a sudden, this helps hugely also with the memory footprint. Instead of storing like huge strings or byte buffers, we use compact integer representation, and that's all we need for verification. And instead of stopping the world for quiescence, we will create a model that will reproduce a system state just from knowing the IDs of the operations that were applied to the database. If you're confused, I'm sorry. There will be a really nice video in a couple of slides that will sort of like make it all intuitive, but I'm sort of trying to build up to it. So let's talk about these points in a bit more detail and see how we can reduce the state that is required for validation to absolute minimum. And here the images start. So we split our system in multiple components. So first one is human-facing. So this is what you are going to be staring at those long nights when debugging the issues whenever your fuzzer finds a falsification. The next one is your descriptor. This is your entropy. This is a unique representation of the value in a form that is going to be used by the model. So this is not something you're going to be interfacing with a lot. And lastly, there's going to be a value itself. So the value that is going to be inserted into the database. It could be any type of value that is supported by it. Different values can be generated from the same generator using different seeds. And values generated from one seed can be of absolutely different types. And our model doesn't really care or is interested in what these values look like. So what's the best about this approach is that you can go back and forth between identifiers, descriptors, and values. In other words, if you query the database, you can infer descriptors, descriptors that were used in order to generate the values that were inserted. So you can go from descriptor to value and from value to descriptor as well. I tried to visualize it in this way. So here we hover over top row, which is our human readable IDs. Then we have a row of database descriptors. And lastly, we have some form of database values that we are using, like we have generated. And keep in mind that you can take the value, you read it from the database, and generate the descriptor from it. And from the descriptor, you can always infer the ID again. So all right, now we have our model. So we have a bunch of queries that are running. Like you can read the query like on the very top of the row. And this is our like internal representation of the database state. So keep in mind that the model only cares about those descriptors. So it only operates with these longs. Even though whenever we're running the queries, you see that we're inserting pretty long strings. Sometimes we would insert an integer for some of the columns, and so on and so forth. So in short, we have several partitions. Within each partition, we have several rows. And for each row, we have several values. And these values are constantly getting updated. Some of the rows are getting deleted. And this is always a faithful representation of the database state that is completely queryable. We support all forms of queries that are supported by Cassandra. So anything that goes there goes in the simulator as well. OK, so using this principle, we can represent queries in a compact way, minimizing the amount of state practically to the entropy that the data was generated from. So we can use even more compact and human-friendly representation to assist humans with the debugging, because it's really difficult whenever you have a very long falsification to deal with all those 64-bit longs, because you just simply cannot tell the difference between two of them, and you're staring at them, and your despair is growing, and I don't want to talk about it. So we can wrap all of these things into a compact and user-friendly DSL and let the users define tests and express some new patterns. In addition, we can include some internal database operations, such as like maintenance, anti-entropy, or some other pattern, whatever you like. And sometimes we would trigger these things in order to induce some more interesting states. So most importantly, we can and probably should include the disasters into the mix, some file system failures, network partitions, delays, crashes, and so on. So all of these are as natural for database testing as insert and updates, even though in reality they are way less probable. So best thing about this approach is that we need only to make sure that our inputs are correct and our model will be able to predict the query results. All right. So it was nice to talk to all of you. We managed to represent our database state. We can generate the data now. We can validate execution results. This is all great, and we should be really happy with ourselves, right? No. Right? 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 So, of course not. We cannot pat ourselves on the back and say that we have done a good job just yet. And our work only begins at that moment. So we have done a lot. So it's been 25 minutes, and we just begin now. So first of all, we need to make our fuzzer not just randomly stumble on the things in the forest, but have a directed path that deliberately searches for novel, cruel things. This can be done in many different ways, but primarily the input generator should be able to distinguish between some potentially interesting paths and some that either have been already pursued and can be considered boring, and some things such as boundary conditions or special values can and probably should be explored first, but after that you may find yourself wondering about other inputs and how deep the edge cases may be found, hiding. So here, instead of using some close-by values, you can use, for instance, exponents or Zipfian distribution or a generator with a distance measure function. The main thing is to try and explore the faraway items instead of the close-by ones. Here, another video. I was trying to represent a partition state. So remember a couple of slides ago, I showed the database state with all those descriptors and queries running on top. Here you can see a workload distribution that evenly splits the number of insert, update, and delete operations, which are represented by the circle pie chart. Okay, pie chart. Sometimes, each row represents a partition. And you can think about, for instance, green items as writes, red items as deleted ones, and blue items as unupdated ones, and so on and so forth. Sometimes you can hit an interesting condition by using simple uniform distribution, but I'm afraid that it is going to get exponentially more difficult as the more you run, because there will be just too much similarity between the runs. So, of course, this is sort of like an exaggerated representation of uniformity. But given enough, large enough data set, probability of hitting any item is going to be more or less the same. This is sort of a definition of uniformity. So that means that producing non-trivial input is going to be difficult. So you can end up producing the results that are not necessarily sufficiently distinct from the ones that you have seen before. Or if they're different, they'll be different in some bold and uninteresting, boring way, and it's not going to be interesting enough to trigger some bug. So this is not to say that you should never use uniform. Oftentimes, like first several issues, your fuzzer will find can be easily triggered with a uniform generator, but over time you will find yourself in a position where your fuzzer will be running for like hundreds of hours without generating any falsification, and this will give you a false sense of security. So instead of this, you can try skewing your distributions and have some way, some very different proportions between the number of queries and have each of the partition exhibit some specific pattern. And now I have a question, like to whom this feels less random than the previous thing? Anyone? So a couple of people, right? So to human eye, I would say the previous slide felt more random, and it may actually be, in terms of like bits of entropy inferred from there, maybe more random. But we are not simply aiming for pure randomness here. So instead, we're aiming for state exploration and triggering issues, right? So that's our goal. Our goal is not to permute our database through the state space of like all 64-bit integers in the world. Because that's going to take a while. So we are deliberately trying to produce the results that look weird and that will stand out, and we use meta randomization to produce interesting patterns instead. So Joran said yesterday that deterministic simulation speeds up time, and my claim is that meta randomization speeds up space exploration. So to summarize, uniform distribution does not necessarily help you with state space exploration. So eventually, you will be getting more of the same thing instead of absolutely different thing every single time. So more complex things may take extremely long time to manifest, so we need something that will speed up the space exploration for us. So we make our generators seek novelty by making them switch modes that we know will explore something new and different. And after that, we control the meta patterns and make our generator produce the inputs that are sufficiently different from the things that we have been producing before. And besides that, we can and should rely on human intuition and try to induce some specific state that a human may have thought about as well. So we can use internal system states for exploration. This is something that many people on this conference have mentioned too. And we can use our knowledge of internals in order to produce the results that will sort of like nudge the system towards the desired, undesired, arguably state. So in order to avoid repeating ourselves like again and again, we can also memorize the patterns and deliberately avoid it. So tell the fuzzer not to explore something like that. And of course, the mode switching and meta patterns absolutely have to include something like time dilation, injecting faults, network partitions, delaying, reordering messages, you name it. And when we're talking about operations in database, this is an operation of the database, however absurd it may sound. So now, we've talked a lot about the fact that we need to generate novel inputs, but the question still remains about how specifically we can do that. So I did mention things like non-uniform distribution and skews, and they're definitely a pretty good way to start with meta randomization. But there are more tools that you can add to your arsenal. For example, using genetic algorithms for novelty seeking. So first, we simply identify the similarity parameters between several configurations. For example, if we're trying to skew the distribution of like a number of columns, value sizes, or proportion of like different types of queries, we can compose a function that receives two test configurations and compares them to one another and produces some form of a similarity measure. If similarity measure yields a value that places the run sufficiently far away from the previous one, we'll keep, like if it doesn't, we'll keep mutating it until it does, right? Because we need something farther away. Now, what's great here is that mutating configurations is an extremely cheap thing. So we can go through like millions of configuration in a jiffy. In order to combine existing, we can also take several runs that we thought that were useful and we have explored them and take them together and combine them into some new run, producing some random permutation of their parameters as well. So another approach that could be used is SMT or satisfiability modular theories. And it's like solver that can be used in order to find a possible solution for situations where only several constraints are known and you would like to find the values that fit the rest of the constraints that you do not know specific values for. For example, you need a combination of sizes of the values that will make you cross the page boundary. So you could compute it yourself, but using an SMT solver, you just code up the formula and it solves it for you. So one unfortunate observation about SMT solvers for fuzz testing is that more often than not, it is not easy to come up with the constraints for the solver after the fact when you already know what the problem is, or let's say it is easy. Like whenever you know what the problem is, you can code up the SMT solver in order to produce the values. But it is slightly difficult to use it for exploration. So one way where it has sort of like marginal use is for generating values outside of some domain. But something like a genetic algorithm might be actually better for this. So in other words, it is good for something like a regression test, but maybe less useful for exploration. So an interesting use case I have encountered that was using SMT solvers was a generation of data inputs that were guaranteed to satisfy certain queries. So in other words, you have a complex query that will return like results only if specific data is present. So an SMT solver in this case helps you to generate the data that will make this query return some results. So another useful application of an SMT solver is to search for like boundary condition. So knowing relations between the items around a certain boundary condition, you can find the remaining unknowns and that can help you to explore them. But for that, you sort of like need to already know which boundary condition you are exploring. So after all, you just want some of the conditions to be random, and the rest can be solved by the SMT, and from there you can infer the rest of the parameters. Anyways, this is something to still ponder upon. So you can think of this exploration as a search in a vast space. So here you can see five-dimensional state exploration. Of course, your test will likely have like hundreds or even thousands sometimes configurables or even more. So this is just for building our intuitions. So you first land in a region that is farther away from the point that you have already explored. And after that, you poke around this region and try to sort of like explore and produce interesting results there. And these clusters can be produced either by mutations, by crossover, or any other form of like genetic algorithm. It's an important thing there is meta-randomization and search, so constant exploration. So in order to help and shorten time of the exploration of the nearby regions, we can also save the system state as of some point in time and return to it if the exploration did not produce the desired result. So instead of starting every query from like ground zero, you can return to the inflection point and continue the search in slightly different direction. So it is also extremely useful for something like shrinking or debugging. So sometimes a test requires a non-trivial setup. So you would be, I don't know, waiting for 5 minutes in order for a condition that is right before whatever you would like to debug is being triggered. So instead, you produce the last known still good state, and then go through the steps and try to understand where exactly it all has gone wrong. So this way you can reuse as much of your test as possible and save a lot of your time. And unfortunately, this may actually require some re-engineering of your system. Gladly, many programming languages, including Java, offer like at least some snapshot capabilities, and they can be useful for this. So your system may require, may have actually already some inherent checkpointing mechanism, and maybe this is something that you could explore for that. And very last thing I would like to mention is regression tracking. So if you have been in a property-based testing, like if you had property-based system for a while in your project, you may end up with one of the two things. Either you have a bunch of hard-coded seeds. Anyone? Like hard-coded seeds? No? Nobody records seeds? So a couple of people do. And the other one is a bunch of tests that manually reproduce the desired scenario. So you know those okay, repro for Cassandra 14731 or whatever. We have many of those. So saving a seed, in my opinion, is often very limiting. Since it implies that all operations within that seed would lead to the same exact output as previously designed. So, but tests will evolve over time, and changes and additions of operation may actually influence the steps during the test, and the seeds may be checking the things that, or may not be checking the things you may think they're checking. So moreover, some seeds may require like extremely long time in order to produce some desired result. This is probably acceptable during the like exploration or testing phase, but you may want a shorter test if you would like to run it on your CI, especially if it's like an interactive pull request one. So hard-coded reproductions are acceptable alternative, but they do not help us with state exploration. And unless they're encoded in some way that allows randomization within this reproduction, we will only so this code will only remain useful for this specific issue and nothing else. So what if, instead of tracking regressions by hard-coding values that our random number generator has produced, we will record a specific meta pattern that has led to the occurrence of some issues. This way, we can use the steps for our evolutionary algorithm. We can exercise some patterns that would inject this specific behavior and maybe surround it with some other things that we haven't thought about previously, and maybe even included in the context of our long-running fuzz test. So for example, a while ago, our fuzzer has found an interesting issue in Cassandra. When you delete ranges of values, you produce something we call range tombstone. Range tombstones have many implications inside of Cassandra for paging, for buffer pool, for merge iteration, and many, many other subsystems. So you're always like one bug fix away from fully getting the tombstones right. So we are for 100%, like just one more issue. So the problem occurs when the tombstone boundaries were split between disk pages. And this bug was manifesting in multiple different ways. Sometimes it would manifest as a silent data loss, and sometimes it would trigger a range tombstone closer assertion. It doesn't really matter what exactly, but it was an exception that the database was throwing at us. So here we use our fuzzer DSL to encode a specific pattern of operations without specifying any details about the queries. Since the bug is agnostic to schemas, it will be triggered in more or less any table configuration modulo some some places where it won't, with any number of columns, and we are just leaving this detail completely out. So here we say that we would visit the partition 1, and visiting partition 1, it means that it is some partition that we call 1. It's just some partition, and we are just going to visit it. And whenever we say that insert to the row 0, we are going to be inserting to the row that is guaranteed to be the first row, or that has the smallest clustering in the data set that is going to be inserted. And 1 is going to sort comparatively to 0, like a greater at. And correspondingly, 2 and 5 are going to be ordered in the same way. So here, whenever we insert the value 0, it doesn't mean that we take 0 and insert it as a value into the database. It is we're instructing the fuzzer to take 0s value from the state space. And that's pretty much all we do. So the fuzzer will create schema, it will create the rows, it will execute all the operations for any conceivable number of permutations of configurations that you want with different configuration settings such as in a big cluster, in a small cluster, and so on and so forth. And all we need to do for validating whether the database output was correct, we just tell the builder, please validate all, and this all sort of happens automatically. So what's great here is that we did not specify any queries, so we did not write any CQL. It's kind of like a Cassandra variant of SQL, but we still made our fuzzer remember about this issue forever. So, and whenever we get a repro, it looks something like that. So we get an expected database state and observed database state, and you can sort of observe the values and understand where they were coming from. So to recap, we were talking about many things today, and we were talking about Oracle testing, and we decided that it is not enough to just have a standby database, and we decided that it would be better if we had some form of a compact state representation. But we decided not to stop at that, and we thought that we need a concept of novelty seeking, and we need our generators to be driven and to start seeking for some interesting permutations of things that we have not run before. In order to save some of our time, we decided to retract and rerun, meaning that reuse some of the state that we have already explored. And finally, in order to facilitate the regressions, we decided that we will track them in a way that is also reusable by the fuzzer itself. And these two books were in order to grok system testing, all you need to do is just read these two books. They're really small, but they are amazing, and they are always sitting on my desk, and I often refer to them. Even though the top book may seem not like a testing book, it really helps you to develop your system thinking. And now for real questions.